Do we need to remove water that collects in the clarifier bowl? Yes, most definitely, or else the water will build up from the periphery of the bowl until it blocks the disc stack. This is a cross-section of the bowl with the water outlet closed. Any water in the oil will be separated and the interface encroaches inwards from the bowl periphery until it reaches the disc stack. Now, some of the water will start to pass out with oil to the oil outlet. How does the ALCAP know if there is any water in the bowl that needs removing? With the transducer in the oil outlet, all the oil leaving the bowl is checked for water content. It does this by using the scientific principle of capacitance that exists in all materials. How can we remove the water that collects in the solids ejecting bowl? We could eject the water with the solids at discharge. This is a good idea until the quantity of water increases and we do not want the bowl discharging repeatedly. We can also use a water outlet from the ALCAP separator the same way as the conventional purifier. Fit a normally closed valve in the water outlet line, which fulfills our requirements for a clarifier, and then open it when water builds up. The ability of a system to store electric charge. The ratio of the change in electric charge in a system to the corresponding change in its electrical potential. Click the buttons to get more information. Capacitance is determined from the equation. With the WT200 transducer, A and D are all fixed, and only a change in the relative permittivity will cause a change in the capacitance. Dielectric constant as is listed. What is capacitance and how can we use it for our purpose? Let us take two plates of conducting material. The area of these two plates, A, is fixed, as we have cut them to size. Fix them with an insulating material such that they are held rigidly a parallel distance from each other. The distance between our plates, D, is now fixed. Now let us imagine an electrical measuring circuit attached to the two plates. Let us now immerse our two plates in oil. There will be a change in response from the measuring instrument. the dielectric constant of the material between the plates has changed from air to oil. Click the buttons to get more information. We could simplify the diagram and show it like this. The change in the measured capacitance will be proportional to the change in the dielectric constants of the air and the oil, that is, from 1 to 2, a change of 2 times. If we only immerse the plates half into the oil, we could consider that there were now 2 capacitors in parallel, one half in air, the other half in oil. Now let us immerse our 2 plates in water. Once again, there will be a change in the response in the measuring instrument. The dielectric constant has changed from oil to water. Click the button to get more information. Now the change in the measured capacitance will be proportional to the change in the dielectric constants of the oil and water, that is, from 2 to 80 for pure distilled water, a change of 40 times. For fresh and seawater, this dielectric constant is much higher, depending on the dissolved mineral content. We will get different capacitance readings depending on the proportions of oil and water between the plates. More precisely, a very small amount of water present will have a large effect on the measured capacitance. Let us make our capacitor more practical to fit our needs. Roll the plates up to make inner and outer pipes. Add insulation to keep the plates apart. Add flanges at either end. By adding flanges at either end, the whole transducer becomes more practical. Add flanges at either end. By adding flanges at either end, the whole transducer becomes more practical. Add the oscillator and the housing. This is what it looks like. Installed in the oil outlet in this way, the capacitance transducer is measuring all the cleaned oil for signs of water content.